Hello everyone. In this video, we're going to talk about analysis of ideal op-amp circuits. The non-ideal case is not going to be very different, or at least the results will not be very different, but assuming ideal op-amps gives us a lot more, makes our analysis much easier. Okay, so when we're doing this analysis, we're going to keep in mind just two rules. One, assuming there is a negative feedback, we will have a virtual short. That means the voltage at the positive or non-inverting pin will be equal to the voltage at the inverting pin. Rule number two, we're going to assume infinite input impedance. That means the current going into the input pins, both the currents I plus and I minus will be zero. Let's look at our first circuit, the inverting amplifier. Okay, so since the current going into the pin, the non-inverting pin is zero, there is no voltage drop across R3. That means V plus equal to 0. By virtual short rule, V minus will also be equal to 0. Okay, so now let's calculate this current I1. I1 using Ohm's law on R1, the voltage drop from left to right is Vi minus 0 divided by the resistance R1. This will be the current from left to right, right? So this will be equal to Vi over R1. Alright, so now since the current going into the inverting pin is also 0, this whole current will also be going through R2. Okay, now let's do Ohm's law on R2. Again, from left to right, the voltage drop is V minus minus VO divided by the resistance R2. This should be equal to the current from left to right, which is equal to Vi over R1. Now V minus is 0, which we saw here. So this implies negative VO over R2 equal to Vi over R1. This implies VO over Vi equal to negative R2 over R1. Okay, so now by adjusting the values of R2 and R1, we can get any gain we want, but negative in value. Okay, so since the gain is negative, this is called an inverting amplifier. Now let's look at a non-inverting amplifier. This time the voltage is supplied at the non-inverting side. Again, using virtual short rule, we have V minus equal to Vi. Now since the current going into the inverting pin is 0, R1 and R2 are basically in series. So since they're in series, I can use the voltage divider rule. Okay, let's use the voltage divider rule. The voltage drop across R1 from right to left is V minus minus 0. So this should be equal to R1 divided by R1 plus R2 times the total voltage drop from right to left, which is VO. Okay, but V minus is equal to Vi. So this implies Vi is equal to R1 over R1 plus R2 times VO, and this implies VO over Vi equal to R1 plus R2 over R1 equal to 1 plus R2 over R1. Again, the gain in this case will always be greater than 1, and by adjusting the values of R2 and R1, you can adjust the actual gain. Now since the gain is positive, we call this the non-inverting amplifier. Okay, now let's look at difference amplifier. Unless the previous cases, now we have two inputs instead of a single output. Now since all the equations governing the circuit are linear equations, so this will be a linear circuit. So that means I can use superposition principle. So first I will set V1 equal to 0. Okay, and then calculate VO1. Similarly, after we calculate this, we'll set V2 equal to 0 and calculate the output voltage and sum them up to get the final voltage. Okay, so let's look at this case. If V1 is 0, if V1 is 0, this is nothing but an inverting configuration where V2 is the input. So that means the output VO1 will be equal to negative R2 over R1 times V2. Okay, now let's look at the case when V1 or V2 equal to 0, and we're going to calculate VO2. Now if V2 is 0, okay, then the input is in the non-inverting side. Now, if you look at the non-inverting amplifier, the output would be whatever the voltage is at the non-inverting pin times 1 plus R2 or R1. Okay, so what is the voltage at the non-inverting pin in this case? V plus will be equal to R2 divided by R1 plus R2 times V1 by applying the voltage divider rule on this series. Now R1 and R2 here are in series because there is no current going into the non-inverting pin. Now if this is V plus, then VO would be equal to V plus times 1 plus R2 over R1. Okay, so V plus is R2 over R1 plus R2, and this term inside the parentheses is R1 plus R2 divided by R1. So this will be there is V1 here. So this one will be equal to R2 over R1 times V1, and this is VO2. So this implies VO2 over V1 is equal to R2 over R1. Okay, so VO1 is negative R2 over R1 times V2, and VO2 is R2 over R1 times V1. So this means my total output VO would be equal to VO1 plus VO2, which will be equal to negative R2 over R1 times V2 plus R2 over R1 times V1, which will be equal to R2 over R1 times V1 minus V2. Okay, so the output is some constant times V1 minus V2. You can adjust that constant by adjusting R2 and R1. Therefore, this now is called, because the output is some constant times the difference of your input voltages, this is called the difference amplifier. Let's look at the integrated circuit now. Again, since the current going into the non-inverting pin is 0, the voltage here would be 0. So that means V minus is also 0 because of the virtual short. Okay, so let's say the voltage drop across the capacitor from left to right like this is Vc of t. That means VO minus V minus VO of t is equal to Vc of t, which implies Vc of t or VO of t will be equal to negative Vc of t. Alright, so then in order to figure out what VO of t is, we need to find what Vc of t is. Okay, so now let's look at the capacitor. If you look at the capacitor physics, the current, let's say if there is a current IC of t going from left to right to the capacitor, then IC of t will be equal to C times the derivative of the voltage Vc of t. Right, because C times Vc of t is the charge and the rate of change of charge is the current, and that's how the physics dictates this equation. So this implies my Vc of t is equal to 0 to t 1 over C I of t dt, or let's say tau d tau. Now notice that in this, when I go from this step to this step, I'm assuming that the voltage Vc of t at time t equal to 0 is 0. Otherwise there will be an extra constant term here. Okay, so let's start with that assumption. In this case, this is the voltage. Okay, so then what is I of tau? If you look at the circuit, the current through this resistor is Vi of t over R. Okay, since there is no current going into the inverting pin, the same current will also be going through C. So I'm going to replace I of tau with Vi of tau over R. That means this equation here, 1 over C, 0 to t, Vi of tau over R times d tau. Okay, so now my VO of t is equal to negative Vc of t is equal to negative 1 over Rc, 0 to t, Vi of tau d tau. Okay, so now what I have is the output is some constant times the integral of my input. So this circuit is actually integrating my input and putting the output putting VO of t is equal to integral of VI of t. Let's look at the differentiator circuit now. Again, no current through R, so voltage here is 0. That means V minus is also 0. So the voltage drop across the capacitance is VI of t. Okay, so let's say the current from left to right is IC of t. Okay, so this implies from the physics of the capacitance, IC of t would be equal to C times the derivative of VI of t. Okay, again, no current going into the inverting pin. That means the same current also goes through the resistance R. Okay, so that now we'll do Ohm's law from left to right on R. So that means voltage drop is 0 minus VO of t. 0 minus VO of t will be equal to IC of t times R. Okay, and I'm going to substitute IC of t from this above equation, which will be RC times the derivative of input. So this implies my output is some constant times the derivative of my input. Okay, so that's why this is called the differentiating circuit. Let's do a quick summary. So in this video, we have seen analysis of inverting amplifier, non-inverting amplifier, difference amplifier, integrator, and differentiator. One note of caution here, when we did the analysis for integrator and differentiator, we assumed the op-amps are ideal, but if the op-amps are not ideal, the circuits won't work exactly the way we are predicting here, so we have to take extra caution, and I would refer you to the textbook to look at the details and discussion about that issues. Finally, I'm planning on adding a lot more videos in the near future, so please subscribe so that you will get notifications of when I add some additional videos. Also, there are many other videos in this channel which may be useful throughout the course, so please feel free to browse other videos. Comments. So if you have any comments on the way I'm presenting, or if you would like to see some changes, please put those put in your comments. And 3, if you have any suggestions about future videos, for example, if there's any particular concept you're finding it difficult to follow, or if it's very difficult to follow in the textbook, please put it as a video suggestion and I will make a video on that issue.